The engineering conference hall in Munich fell into shocked silence. It was 2019 and structural engineers from across Europe had gathered to discuss sustainable bridge design when Dr. Maria Reyes, a Filipino civil engineer, presented her research on traditional bamboo bridge construction. The room erupted in condescending laughter. "Bamboo," scoffed Dr. Klaus Hoffmann, Germany's leading bridge architect, his voice dripping with mockery. "You're presenting bamboo as a viable structural material at an international engineering summit. This is embarrassing." He stood up, gesturing dismissively at her presentation. Bamboo was a temporary material. It rots, it weakens, it fails. There's a reason we use steel and concrete, because they work. Other engineers nodded in agreement. A French architect added, "Perhaps this is acceptable for rural villages. But we're discussing real infrastructure here, modern bridges that carry real loads, real traffic, real responsibility." Dr. Reyes remained calm, her hands steady on the podium. She had expected this for years. Western engineers had dismissed traditional Filipino construction techniques as primitive, temporary, inadequate for serious structural work. What they didn't know was that she was about to show them something that would shatter everything they thought they knew about engineering. "Dr. Hoffmann," she said quietly, advancing her presentation to the next slide. "What if I told you there's a bamboo bridge in the Philippines that has been standing for 120 years? Not just standing, thriving, carrying thousands of people daily, surviving typhoons that destroyed modern concrete structures around it. Would you be interested in examining why?" Dr. Hoffmann laughed again, but this time with less confidence. "Impossible. Show me the engineering reports. Show me the maintenance logs. Bamboo doesn't last 120 years under structural load. It's scientifically impossible." Dr. Reyes smiled. "Then perhaps, Dr. Hoffmann, you should come to the Philippines and see it yourself. I'll arrange everything. Bring your instruments, your testing equipment, your entire team. Examine it thoroughly. If I'm wrong, I'll withdraw my research. But if I'm right," she paused, "you'll need to reconsider everything you know about sustainable engineering." The challenge hung in the air. Dr. Hoffmann couldn't refuse without losing face in front of the entire international engineering community. "Fine," he said truly. "I'll come, and when I prove this is either falsified data or a temporary structure on the verge of collapse, I expect a formal apology." 3 months later, Dr. Hoffmann and his team of 5 German engineers arrived in Bohol, Philippines. They brought advanced structural analysis equipment, moisture meters, stress calculators, and every testing device modern engineering could provide. They were confident they would expose this bamboo bridge myth within hours. The local community led them through winding rural roads until they reached the Bambang hanging bridge spanning a deep gorge in the mountainous region. Dr. Hoffmann stepped out of the vehicle and froze. The bridge stretched before them, graceful, impossibly delicate looking, constructed entirely from bamboo poles bound together with traditional methods. "This, Dr. Hoffmann said incredulously, "this is your miracle bridge." He approached cautiously, examining the structure. The bamboo was weathered, but showed no signs of the rot he expected. The joints were secured not with modern fasteners, but with traditional rattan bindings and wooden pegs. "How long did you say this has been here?" asked his assistant, Dr. Weber. "Taking moisture readings, 120 years, answered M. Thomas, the elderly bridge keeper. "My great-grandfather helped build it. I've maintained it my whole life, as my father did before me." Dr. Hoffmann shook his head. "Impossible. Bamboo degrades. This must be a replica. You've rebuilt it multiple times, haven't you?" "That's the only explanation." Meng Thomas smiled patiently. "No. Engineer, the same bamboo. We know how to treat it, how to select it, how to position it. Our ancestors understood things your modern science hasn't discovered yet." The German team spent the first day taking measurements. They tested load capacity, checked for structural weaknesses, analyzed the bamboo's composition. Every reading confused them more. The bamboo showed minimal degradation. The joints remained incredibly strong. The entire structure demonstrated engineering principles they couldn't fully explain. "This doesn't make sense," Dr. Weber muttered, reviewing his data that evening. The moisture content is perfect. Too perfect. Bamboo in this climate should be rotting. Instead, it's almost perfectly preserved. How? Dr. Hoffman refused to admit confusion. There must be chemical treatments, modern preservatives applied recently to fool us. On day 2, they took core samples for laboratory analysis. They examined the rattan bindings under microscopes. They studied the traditional joinery methods that use no nails, no screws, no modern fasteners, just precisely cut bamboo, wooden pegs, and plant fiber bindings that had held firm for over a century. The results stunned them. No modern chemicals, no preservatives invented in the last 100 years. Whatever protection the bamboo had came from the traditional preparation methods. Methods passed down through generations that Western engineering had dismissed as primitive. Superstition. They smoked the bamboo, explained Meng Thomas. Watching the engineers work, specific woods, specific temperatures, specific timing. Then we cure it in salt solutions made from local plants. We position each piece according to the sun, the wind, the water flow. We learned this from our ancestors who learned it from theirs. Smoking and salt, Dr. Hoffman said dismissively. That's not engineering. That's folk tradition. And yet, M. Thomas replied gently, your modern bridges, how long do they last? 30 years, 50. Before they need major repairs. He patted the bamboo railing affectionately. This bridge has seen 120 typhoons, each one destroyed something modern nearby. The bridge remains. On day 3, the real test came. Dr. Hoffman insisted on stress testing. We'll prove it's weak, he declared. We'll find the failure point. They brought in weights, measuring exactly how much load the bridge could handle before showing strain. The calculations were precise. Based on bamboo's known properties, the bridge should start showing stress at around 3,000 kilograms distributed load. They loaded it with 5,000 kilograms. The bridge barely registered the weight. They increased to 7,000 kilograms. The structure held perfectly, showing less deflection than Dr. Hoffman's calculations predicted. At 10,000 kilograms, far beyond what any engineer would consider safe for a bamboo structure, the bridge continued to perform flawlessly. Dr. Weber stared at his instruments in disbelief. Klaus, this is impossible. According to every engineering principle we know, this structure should have failed 3,000 kilograms. The bamboo should be splintering. The joints should be separating. Something should be giving way. Dr. Hoffman had no response. His face had gone pale. Everything he had built his reputation on, his certainty about materials, his dismissal of traditional methods, his confidence in Western engineering superiority was crumbling like the concrete structures he championed. On day 4, a violent storm rolled in. The local officials urged everyone to evacuate. But Dr. Hoffman insisted on staying. I want to see how it performs under real stress, he said. This is the test that will reveal the truth. The typhoon hit with devastating force. Winds exceeded 150 kilometers per hour. Rain fell in torrential sheets. The gorge below filled with raging flood water. The German engineers huddled in a reinforced observation post, watching the bamboo bridge through the storm. The bridge moved. That much was clear. It swayed and flexed with the wind, bamboo poles bending in ways that would snap rigid materials. But it didn't break. It danced with the storm, absorbing forces instead of resisting them, flowing with nature instead of fighting it. It's not trying to be stronger than the storm, Dr. Weber observed, mesmerized. It's designed to work with the storm. Flexibility as strength, movement as stability. This is revolutionary. When the typhoon passed, the bridge stood and changed. Meanwhile, reports came in of modern structures damaged throughout the region. A steel pedestrian bridge 3 kilometers away had twisted off its foundation. A concrete overpass had developed critical cracks. But the 120-year-old bamboo bridge remained perfect. Dr. Hoffman stood in the morning sun, staring at the structure that had humiliated him. He approached Meng Thomas slowly, his earlier arrogance completely gone. I don't understand, he admitted quietly. I've studied engineering for 30 years. I've designed bridges across 3 continents. I've taught at the finest universities, and I cannot explain how this is possible, Meng. Thomas smiled kindly. That's because you were taught that engineering is about conquering nature, making things stronger, harder, more resistant. Our ancestors understood different wisdom. Engineering is about harmony with nature, understanding materials, not as things to force into service, but as partners with their own properties, their own strengths. The German team spent 3 more days documenting everything they could. They took extensive photographs, created detailed measurements, interviewed local craftsmen about traditional techniques. They left the Philippines, changed men, back in Munich. Dr. Hoffman did something that shocked the engineering community. He published a formal paper titled, "What a 120-Year-Old Bamboo Bridge Taught Me About Engineering Humility." In it, he documented everything he had witnessed and made a stunning admission Western engineering had lost crucial knowledge in its rush to modernize. The paper went viral in academic circles. Within months, engineering programs across Europe began incorporating traditional building techniques into their curricula. Sustainable architecture firms started consulting with Filipino engineers about bamboo construction. Dr. Hoffman himself became an advocate for studying indigenous engineering methods. Dr. Reyes was invited to present at conferences worldwide. The bridge in Bohol became an international destination for engineering students from MIT. Cambridge and Tokyo University came to study the structure that shouldn't exist according to modern engineering principles, but had outlasted nearly everything modern engineering had built. Today, bamboo is experiencing a renaissance in sustainable architecture. High-rise buildings in Singapore use bamboo reinforcement. Bridges in South America incorporate Filipino traditional techniques. The material once mocked as primitive is now celebrated as the future of sustainable construction. But perhaps the greatest change happened in Dr. Hoffman himself. He now teaches a course called Engineering Wisdom, what traditional builders can teach modern engineers on the first day of class. He shows his students a photograph of the Bambang Hanging Bridge and tells them a story about the day he learned that sometimes the oldest solutions are the most advanced. Meng Thomas still maintains the bridge as his family has for 4 generations. When tourists ask him about the famous engineers who came to study it, he chuckles. They came expecting to teach us engineering, he says. Instead, the bridge taught them.